Thank you for being here. It's a pleasure to have Anne and Bill. They'll be telling us about extreme value theory from a geometric perspective. It's something they've mentioned in talks throughout the years a few times, and I've always been curious to try to understand what's going on under the hood with these calculations. They seem very interesting. And, well, I'm very pleased that they're here today to tell us a bit about it. And this is going to be a mini course, so there'll be more lectures forthcoming. So, without further ado.
Well, thank you for the invitation to do it. We've been working on some of these things for more than 10 years. But since we've been doing it in a commercial setting where there weren't as many and we've talked in many academic venues about some of these things, but the pressure is to make money to pay the bills, not to publish papers and so on. And some of it we've had to keep confidential for commercial reasons. And we're hoping that will perhaps change shortly. Anyway, the part that I'll talk about today is an introduction to these ideas, and in particular the geometric method that Cartan introduced that allows us to get surprising insights into the subject without knowing anything about it, if you like. So this is another example of this is that using Cartan's approach, you could have discovered the Gauss curvature without knowing anything about surfaces. You didn't need any of Gauss's insights to discover that the curvature was an intrinsic property. You could have discovered it, and you can do it. You can see it in a few lines, in fact. So this is typical. I discussed this briefly with a statistician, Anthony Davison, who's an expert in extreme value statistics, among other things. And he was, his remarks were, well, there's a conservation of work involved. So you labor to get to the top of some peak, and you can look down on other things and see things that you would never have seen otherwise. Or you could climb the other mountain and discover them in another way. And that's true. There's not it's not just number theory where there's no royal road. But of course, the fact is, once you know these things, you can apply them in other places. You don't have to discover them. We'll show you a couple of invariants that have very significant applications and the way they're discovered. So today I'll talk about this use of geometry through the transformation of the location scale group, the affine group on the line, and the way that Cartan's methods turn that into invariance. Which this example is nice because it's simple enough that you can see everything with rudimentary calculations. So you don't have to depend on any grand theorems. You can actually check that all the claims are true. These are calculations you can easily do. But the results are quite powerful. And then next week, Anna's going to do the lecture about a related but not immediate, sort of slight diversion of a subject called the theory of omega functions. It's something we developed over a long, long time now, well over 10 years. But this is a natural way of describing distributions for the subclass of distributions that have a finite mean. If you have one first moment, then there's something you can do that you can't do otherwise. You don't, and you get bonuses again. For example, there's an intrinsic measure of distance from the mean without variance, without a second moment being defined, right? And so on. So that's a subject which it also has the property that the that it's quite geometric in nature. That is, gives you a picture of a distribution as the cumulative does. I'm assuming everything's smooth here, right? For us, two continuous derivatives are going to be available. We'll come back and talk a bit more about the restrictions or not lack of restrictions that really puts on. But this picture of things has a geometric context. It knows where the mean is. And its slope at the mean is what gives you this intrinsic measure of spread around the mean. So this is a lot of bonuses for the restriction of having a finite mean. And for most, I mean, in practice, since if you're doing statistics, you're using samples, and samples always have a finite mean. Right? Even if you're drawing IID from a Cauchy distribution, the sample will take a long time to teach you that. Right? It will have a mean. So it's a very natural restriction. And again, these are things that weren't discovered until the 21st century, but could have been done by Gauss. So there's a lot of interesting stuff, sort of low-hanging fruit, if you like, that's been left unpicked because nobody stumbled across these ideas before. And one of the things that comes out of it comes from a natural deformation theory of these objects. And using the methods from today, we'll see that there's a whole new class of, there's another limit, a new limit theorem that's previously undiscovered that's quite powerful. And there are applications to many things, including numerical analysis. So that's a sort of brief picture of where we're going. The details will fill out the next lectures. We'll come back after the omega function things into something that will unify the two threads and prove some new theorems about extreme value theory. First of all, you can unify results that were discovered over a period of 75 or 80 years, but there's more as well. Okay. Doesn't want to go. What's happened? There we go. Sorry. Okay, so you may have heard this expression from Felix Klein, the Erlangen Program. This says, well, what is geometry? Well, at the end of the 19th century, geometry in Felix Klein's summary of it was all the properties of a space that are invariant under the transformation group. So a transformation group determines geometry. Now this quite quickly became absorbed and missed at the same time, if you like, in modern differential geometry. But in this period with the discoveries of Lie and the uses of symmetry, transformation groups, and attempting to solve differential equations, and then the extensions of Lie's work that Carton did, this was very much mainstream at the end of the 19th century and the beginning of the 20th century, something everyone would have been aware of. And Carton managed to extend this beyond the idea of the geometry of a space to geometry determined by objects like a differential equation or system of differential equations or a probability distribution. And he gave a method for extracting the geometry, getting out all of the essentials of the geometric information through a computational process. So in statisticians speak, these are the group we're interested in is the location scale transformations, the affine group on the line. And that, of course, is the source of all of the two parameters you see in the two parameter families of distributions in all the statistics textbooks. There's always at least two. One of them tells you where the location and the other the scale of and of course probability is intrinsic, right? It's not different on different scales and locations, right? So the action of the affine group, I mean, it's almost tautological. We're just taking any distribution, for example, any normal distribution, pick your parameters. Then the affine scale group acts on that one. It's transitive, right? It gives you every other one. So that action seems incredibly innocuous. Right? But in fact, it has real information in it. There's in particular, there's a differential an invariant under that action, which allows you to comb out classic cases. And we'll get to that today. Okay. So this actually, because this developed over a long period, we actually had results about extreme value theory before we even knew what extreme value theory was. As we hadn't, well, I had once, I guess, in about 1998, I think there was a recently published book on extreme value theory by, I've forgotten his name. He's at ETH. He's Embrechts, Paul Embrechts, with a couple of collaborators, had published this book, and I picked it up and I thought, this seems nuts. Right? You're actually saying you can see into the tails of the distribution where you've got no data. And then that's very intriguing, but it's a book that only an analyst or an actuary could love. I mean, it's very, very dense. And I'm neither of those two things. We're from the geometry world. Well, that's an interesting thing. Where we started to get intersect with this was after the great financial crisis crash hit in 2008. And at that point, we looked at what the things we had been using would have told us about the riskiness of big banks and so on. And it was alarming. You could see the risk levels were going up dramatically all through late 2007, way around. And the crisis didn't hit till September 2008. So what we saw was that these techniques gave you warnings way in advance. And then we said, well, where were all the extreme value theory people? Why didn't we see them saying, look what's going on? And the answer became clear after a while. It was that they needed so much data that they didn't get the warning when we did. We had a way of doing this that required far less information to process. And that's something that we've come to understand much better. So once, I remember explicitly, I think I remember explicitly going through some of these things in a cafe in London and checking some of the theorems and looking back over some of the older results, the classical results, papers by Gidenko and so on, and becoming more and more convinced that there was something important going on. And then eventually, we got a new proof of the extreme value theorem and much more. And so we're going to give the proof of that in the course. And I hope also we'll be able to present some new results on Levy stable distributions. So it's another place where you don't have to climb the mountain that Levy did to discover the stable distributions. So now that's a little more complicated, and we're still sorting out some of the differences. So Cartan's approach to transformation groups was always through differential systems, differential equations, but expressed in terms of differential forms. That was natural, but a little different from what Lee had done. Lee had taken this, the definition of transformation groups at the time was that they were solutions, a general solution of a certain type of differential equations. That was the world, right? you can look at those things through vector fields, or you can look at them through forms. And Cartan's method was to look at them through forms, where Lie and his other contemporaries were using vector fields. So the idea is to turn a group into maps that preserve a set of one forms. Okay, now that's very easy to do in this particular case. The affine group on the line is here. We have A greater than 0. Probably Cartan would have said just A not equal to 0. So it's invertible and not cared about the orientation reversing things. We're going to look at the class where A is 0. But basically, that's the general solution of y double prime equals 0. Okay. And I gave a lecture in February of 2020 that's on the YouTube channel about Cartan's methods. It says more about this process. So there's an algorithm that he goes through to do that. But we'll see that you don't, in this case, you don't need the algorithm. You can see that everything's there. So we're going to look at R2, coordinates x and p. This is an artifact of the algorithm. It's the fact that the p is there, not a y. This is actually a restriction of the jet space where it would be x, y, and p, and you'd be thinking of things that satisfy dy minus p dx equals 0 to link p to the derivative of x, right? And then dp equals 0 would be the differential equation. But Cartan is a method of getting rid of that. So we'll just start with these two one forms. And the claim is the affine group. Except for the fact that they're in forms instead of vector fields. It's the same. This part is the same as what Lie did. Okay. But the real difference comes as soon as you're dealing with infinite pseudogroups. The structure equations method and the vector fields methods, well, intrinsically they're talking about the same thing. So there has to be a map back and forth, but it's not fun to try to make it. So the claim is that group is just the things that preserve the maps of R2 to R2 that preserve those one forms. So what I mean is if I've got, there's my transformation, x bar and p bar are the new coordinates. So I make a theta 1 bar and a theta 2 bar out of those coordinates exactly the same way as I did to begin with. And then the condition is that the two theta 1 bar is equal to theta 1, theta 2 bar equals theta 2. Okay. Well, these are differential equations. It's easy to see what the consequence of them is. Okay. In coordinates, p bar dx bar is p dx, dp bar over p bar is dp over p. Okay. Well, first of all, although x bar depends in principle on both x and p, there can't be any p dependence. Because if there was, this equation couldn't hold. There'd be a dp term. Okay? And there isn't. So that tells us immediately that phi depends only on x. But then the second equation tells you that it must be a constant, phi prime must be constant. Otherwise you get a dx term in the equation that only has dp's in it. So you get these two conditions and that together, phi double prime is 0. So phi is ax plus b. So that says that if you've got something that preserves the differential forms, it has to come from an affine transformation. The converse, you can check. That's exercise 1. That if you extend the transformation on the line to R2 by this rule, then you automatically preserve theta 1 and theta 2. Okay? And of course, there's two. We have to be in 2 dimensions or higher because we've got 2 degrees of freedom in this group. So this is, I should have made this another exercise, I guess. But anyway, the Cartan's approach to subgroups, and this is critical when he was talking about the classification of the infinite transformation groups, that was his goal in doing all of this. And that's to, the group starts by preserving a collection of one forms, and then the subgroup will, in addition to that, preserve a bunch of invariant functions. That's how you cut down from the group to the subgroup in the general case. So it's easy to check this. You should do that exercise if you're interested. What are the subgroups? Well, the translation and the scaling subgroups, and they're determined precisely as the things that preserve these two invariants. That's easy to check. So now we want to apply this to probability distribution. So now it turns out to be very convenient to use the log of the distribution instead of the distribution. And we're adding to the conditions that preserve the group the fact that I bar is equal to I. Which is, I mean, this is literally just saying that F bar is F composed with the transformation. That's it. But this is not, this has consequences. Okay. And the first thing is, since exterior derivative commutes with smooth maps, you just take the exterior derivative of everything in sight. Right? D squared equals 0, so there's a limit to what you can do with this in finite dimensional spaces. And so the first thing we do is take the exterior derivative of I bar and I, and they must be equal as well. That's a consequence of the first condition. But now there's something in there, because if we compute di, we can express it in terms of dx, but we want to express it in terms of theta 1, so we've got a multiple of p to take care of. So there's a function of x and p that satisfies di is k times theta 1. Since di is preserved, theta 1 is preserved, k must also be an invariant for this transformation. And k is just, commas, I'm going to use commas for derivative. So it's the first derivative of I with respect to x over p. So the mantra is always the same. You do everything that you did with the unbarred variables, you do with the barred variables. So k bar has to be defined in exactly the same way, because if it doesn't line up with k, which is an invariant, you can't have the transformation you're looking for. It's a necessary condition that k bar is equal to k, and also dk bar is equal to dk. Now the useful thing here is not to compute dk, but to compute its logarithmic derivative, because that very quickly allows you to finish the calculation. So there's the calculation of d of log k. It splits it into d of log ix and d of log p. So that's just ixx over ix. Sorry, I've missed the commas in some of these derivatives. Dx minus dp over p. Dx isn't preserved, but theta 1 is, and it's just a multiple of dx. So we adjust the numerator and denominator to get that multiple out, and we end up with some function times di minus theta 2. So j here must also be an invariant. Everything in these equations is now lined up. We're using only on a basis of invariant forms and computing exterior derivatives, so the coefficients must also be invariants. And here, I mean, obviously, j is just the second derivative of I divided by ix squared. So that has I mean, if you go back to use f instead of I, you'll see a familiar looking combination too, but this one's simpler to write down. But the thing is, j only depends on x. We were up with k, we're up in R2. We've got dependence on both x and p. But j depends only on x. So it has to be functionally dependent on I. I's a perfectly good coordinate function. Right, we've got another function. We have to be able to express it in terms of I. Right. So that functional dependence is the remainder of the information in this classification. It completely characterizes the equivalence class. So once we've got these things lined up, I bar is I, K bar is K, we check, is J bar the same function of I bar that J was of I? If it is, we're done, and it's an exercise to check that. So that's the orbit under the group. Under the affine group, everything that you can get to from F. Yeah. Yeah. Yes. So, and then you can check, you get both the uniform and the exponential distributions are going to give you a constant function for h. Right? They have to be different because you can't turn an exponential distribution into a uniform by changing the location and scale. They didn't have to be constant. Generically, they're not. The fact that they're constant for these two distributions tells you those distributions are special from the point of view of the geometry. They're exceptional. Generically, h will not be a constant function. Oh, so for another exercise, compute h for the normal distribution. It's just a big mess. It's an invariant, but it's not constant. Okay. So now we've solved the equivalence problem, actually, except for the fact that we knew it was okay to take the logarithm of f. We didn't use the fact that f was a probability distribution. It was just a function, okay, with two derivatives or more. So if instead of looking at a function, we look at its powers, we can ask, when does that stabilize under affine transformations? So when is it the case that if I take any power of g, it's up to a location and scale transformation the same as g itself? And we'll see that that let's say y in a bit. We'll see that that's the key to the extreme value theory. So think of lambda as an integer. Extreme value theory starts by looking at powers of a distribution. If you think about distributions that are Levy stable, the product of the characteristic functions a number of times has to be up to affine transformations, the same as the characteristic function you started with. Right? So these things, this comes back again and again, and it will also come up in our discussions of omega functions. And it's sort of there's one problem here. The solutions look different because of the nature of the difference between distributions and characteristic functions and omega functions. But there's one equivalence problem. We've solved it. We can use the invariants that come out of it again and again and again. This was something that we really something that I really had to start thinking about when I, over lunch with Mauricio Peixoto one day, I was explaining to him what was going on here, and then he asked a question, and I realized, which happened fairly often with Mauricio, but he asked a question that made me realize I wasn't quite as well informed about the subject as I thought I'd been, and I found something that quite puzzling that we solved while we were still here. I remember we were in the Praça Sibelius in Gavia when we realized what the answer was, but it was Mauricio that prompted the question. So what is the condition, what is the thing that we've just solved, the equivalence problem we just solved, tell us? It tells us that if you compute J for this power, G lambda, it's going to have to be the same function of I for G lambda that J was of I. That proof had nothing to do with the nature of G, except its differentiability and positivity. Right, so it's easy to check. Right? What happens when you take the power of g? Well, I is the log of that power, so it's just lambda times the log of g. So, and then if you differentiate, you see you get a 1 over lambda when you get j. So the stability question condition holds precisely when you have this one parameter family of conditions on lambda. So we're thinking of lambda as a deformation here. What's the natural thing to do? It's to take the derivative at the identity, right? When lambda is equal to 1, you've done nothing. The tangent at the identity is always a good thing to look at. It's the Lie derivative. And so it's the exercise, the next exercise is to check equation, check that equation 11, that equation 11, it's got a typo here. It's check that equation 11 forces equation 12. So you just differentiate and evaluate at lambda equals 1. See that condition says that the relationship is no longer arbitrary. It's got to be a constant divided by I. That's it. So you've got a one-parameter family, the parameter being C, of these things, but that's all. And notice that that condition, like the condition that J equals H of I, that's a second-order ordinary differential equation. We've got two derivatives. And the general solution of that, the two arbitrary constants, are the two parameters you're going to see at the end. Right? They're the group parameters. But they're also what you get by integrating these differential equations. And then, of course, now it does matter whether G is a distribution or an omega function or a characteristic function, because that will determine the nature of constants C that are allowable. Not everything is possible. But one thing is interesting here, and that's immediately the way that lambda fits into these two things means that in the product it disappears. Okay. So you actually have an invariant that's got nothing to do with lambda. And we'll see later on that an awful lot of, well, in fact, the theorems of extreme value theory, although you start off by looking at powers, integer powers of a distribution, the result has nothing to do with those powers. Nothing. They're gone. Okay. It has only to do with the asymptotic shape of the tails of the distributions. That's it. So that will come later. So here's the quick guide to extreme value theory. So the first papers about this were actually, I think, predated Fisher and Tippett. There was work by Richard von Mises, the younger brother of the economist von Mises. For sure. And of course, as in many things in mathematics, the people whose names end up on the objects were not the people who discovered them, not by a long shot. But anyway, Fisher is the famous statistician, Fisher. And Tippett worked in applied statistics. He had written some things about these ideas before, and the problem he was studying was breaking strength of cotton fibers. He worked for the Cotton Institute in England. This was 1928 when they. So it was published in Philosophical Proceedings of the Cambridge Society in 28. I have no idea what the lag in publication was. Probably not that great in those days. But the discovery was around 1928. So here's the formal description. Start with n independent, identically distributed random variables, distributed with f. Then start looking at the maxima of these samples. Well, if it's easy to see what the distribution of the maxima is. It has to be f to the n. Okay. So their idea is to start looking at this as n goes to infinity. Well, if you do that on your favorite symbolic manipulator program, you get a Heaviside function pretty quickly, right? You just can't see the difference between that and your distribution to the nth power as n gets bigger. But of course, if you stretch it out, and sometimes you want to translate it as well, if you stretch it out with an affine transformation, it starts to look like a distribution again. Okay. So their question was, what's the limiting distribution as n goes to infinity, if there is one, up to transformation by location scale group. And they did something quite sensible. It's a horrible paper. I photocopied it page by page in the archives of King's College Library in London. And then I didn't read it all because it was just it's very, very dense, and it's all functional analysis, basically. In a way, to get away from the fact that n is discrete and not continuous. Right? So anyway, but if there's going to be a limit, then that distribution has to be its own limit, right? That's their intuition, and what they did was not to solve the problem of what every distribution ends up looking like, but say, what are the possible limits by solving this? What are the things that are their own limits? What are the things that are stable under this deformation? Okay. And it's quite remarkable. There are only 3 families that satisfy this. So the first, here they are in the parameterization that they gave, which is not the best one by any means. The first one's now attributed to Weibel, who I think certainly had nothing to do with this. Frechet probably discovered the Frechet distributions. And Gumball came much later, so didn't discover this either, but he made it quite, popularized it in a lot of applied work in the 30s and 40s, if I remember right. Okay. So there's one parameter here. And this is the only thing you can have. Now, of course, you can translate these around. It turns out there are better ways to write this on variable domains instead of on fixed domains, which we'll see. But those are the 3 types of distributions. And they're clearly distinct, right? There's no overlap here. And if there's going to be a limit, it has to be one of those. Now, this was a big accomplishment to go prove this, find these things. But it didn't solve the problem, for example, of knowing what the limit was. If I walk in with a distribution, what's the limit? Well, basically, you have to do exactly what they did all over again, right, to discover it that way. But it's easy to see, in terms of the invariant we've discovered, what these things look like. Right? For the Gumball distribution, ij is equal to 1. It's a constant. Okay. So the Gumball distribution isn't just something that shows up in Fisher and Tippett's fever dreams. The geometry put it there. Okay? If you're a geometer, you say God put it there. Right? It's intrinsic. It's exceptional. There are only a handful of, it's like, in fact, there are 3 there. The 3 is exactly like 3 kinds of constant curvature surfaces. There's negative curvature, positive curvature, 0. And even though this is a 1, the parameterization, this is the flat one. This is the 0 curvature analog. And it is a direct analog because we're looking at an invariant as second order in the derivatives of the original data. Right? It's very much like a curvature. Okay, so the exercise to work out what the constants or what the invariants are for the other 2, and they're all constants. So that's what's special about the from a geometric point of view, that's how you find these exceptional distributions. You just look at the equivalence problem, not for nth powers, but for lambdith powers, which in fact was what Fisher and Tippett were basically doing. And they were criticized heavily, and I think Gdańko was the one who, he did his work without knowing about theirs, but afterwards he pointed out that, you know, there was no excuse for treating n as though it was a continuous variable, which, I mean, fair enough, right? But it turns out not to make any difference. And then, yeah, it was von Mises, but look, 8 years later, he actually was able to show that this is a one-parameter family. And you do it by shifting the domain, making variable domains instead of fixed ones. And then it makes it easy to see that as the parameter tends to infinity in either positive or negative, you end up with the Gumball distribution. So it's the limiting distribution of these other two families. Oh, so I'll just say a couple more things about that before. So the next big result in this field wasn't until the middle of World War II, where Gdańko managed to, heaven knows how, I think he published a paper in the Journal of the American Mathematical Society. Now, it must have gone via the polar route. There was Russia was being supplied via Murmansk or someplace across the North Atlantic. But, I mean, absolutely extraordinary. He was able to get this paper in the middle of a horrific war, able to get this paper out of the Soviet Union and publish it in the United States. And Gdańko had just, he had shot his mouth off about the Soviet system in the hearing of people who were reporting to the commissar, and got thrown in jail for a while. And I think it was Kinchin or maybe one of the other big names managed to get him out. And then he got really lucky because he was regarded as politically unsatisfactory, so they wouldn't let him into the army. So he managed to survive. And this paper is a real tour de force, but you look at it and you see that nowhere does there seem to be these integers showing up. Right? It's a paper about asymptotic behavior of things that are literally the shape. And we'll see later, he was never happy about his conditions of discovering when was a distribution going to be equivalent to the Gumball distribution. The other two he had nailed down. The other two depend on the scaling symmetry, and the Gumball one depends on the translation symmetry, which he wasn't. I mean, his methods are clearly designed for scaling. And so, well, again, we'll come back to see that later. Okay, so if you look at any account of extreme value theory, people will start off by looking at the problem we listed first, nth powers of a derivative of a distribution arising from taking the largest of a sample of n independent variables and doing it again and again and again. And then they jump to something totally different. Well, we're doing something similar, but in the opposite direction. They look at conditions being above, peak over threshold, they're called, where you're looking at a distribution conditional on being above a fixed threshold, and then looking at what happens as that threshold's allowed to go out to its limiting value. We're going to do it the other way, which turns out to be very useful. So Anna decided we should call these peak under threshold stability. So and it's very simple to write down, right? We're just looking at a distribution on an interval from A to B where either A or B might be infinite. Pick a point in the interval, and now look at the distribution conditional on being less than that that level. Right? Well, it's just, of course, that's what the distribution, the conditional distribution is. Now the question is, when is that equivalent to the original distribution up to a change of variable? And you can see things like the exponential distribution, just sliding over, right? You've still got the same, exactly the same thing, rescaled, right? That's obvious, right? And so on. So, but what are the rest of them? Well, this is the exercise. The condition is simply that J be a constant. That's why I said the first exercise was compute J for the uniform and the exponential distributions, the constant in both cases. So they're among these distributions that are peak under threshold stable. And it turns out that there's a very important duality between these things and the extreme value distributions. So there's a one parameter family of these things. And if these look familiar, or vaguely familiar, it's because they're essentially the generalized Pareto distributions. So I call these things mirror images, which has confused some my statistician friends in the past. But if you think about a distribution that has a probability density function, then there's always a mirror image of that density function. And there's a probability distribution associated with that, and that's what we're calling. And so, of course, it's not just given by putting x equal to negative x, but that mirror image is given by f hat at x is 1 minus f of minus x. Okay. And if you apply that to the distributions I wrote here, you'll see that what you've got is the family of generalized Pareto distributions. Okay. And that one parameter lines up exactly with the parameters in the extreme value theory, which is one of the magic things that gets pulled out. Well, I'm pulling it out of the hat here too, right? But in fact, we'll see that it's actually a geometric duality between these things. There are only so many constant curvature objects. Looking at peak under threshold stability tells you you're looking for those. And here they are. Now, it's not going to be, it will turn out that if you knew about these, you could discover the extreme value distributions and conversely. So this is another one of these examples where you get a lot of things for nothing. Well, for nothing. I mean, actually, for what turns out to be a modest investment in equivalence problem solving, you get all of these results. Now, the thing is, it's not that you can't, if you try to read about the equivalence method, you'll find the same kind of problem you find getting into extreme value textbooks. There's a lot of work that has to be done up front. But now it's been done, right? So you can use this invariant. You don't even need to remember how it was found. Right? You know it's an invariant, and you can use it. And it has a lot of important consequences. And we're still unearthing some of them. So here's the modern version of the extreme value distributions. I stick them all together with a limiting case being the Gumball distribution. And you can see where the limit as alpha goes to infinity is going to give you the exponential function. And now, of course, the benefit of this is as alpha in absolute value goes to infinity, you get the real line, right, as the domain. And there, it's much easier. I mean, I find it slightly awkward thinking of the thing being a limit, of having the limit as a Gumball distribution when it's been defined on a half interval, and so on. But so this is a way of easing your mind about that, if it bothers you. Right? What am I? Which way do I need to point to make this work? Sorry. No, I just want to advance it. Sorry, desculpa. Careful. Ah, desculpa. No, you're right. That's the last exercise. I'm sorry. Yeah, no, that explains it. So I want to say a few more things while that slide is still up. So what we've demonstrated is the constant invariance, this constant for this product, I and j, is what picks off the extreme value distributions. The constant for j is what picks off things on the other side of the world, if you like. And what we'll show a little bit later is that that's enough. Those conditions are enough to know when you're in the domain of attraction of an extreme value distribution. So the idea is, if I have a distribution like the normal distribution, when I look at its powers, or I look out in its tails, what I see is it's getting closer and closer to the Gumball distribution. How do you see that using invariance? Well, in fact, it's very easy, because you compute the invariant ij for the normal distribution, which is a messy formula. But now all you have to do is look at its limit as x goes to infinity. That limit will go to the Gumball distribution, constant. If it does, that's in the domain of attraction. If it doesn't, it's not. Right? Now, there are Richard von Mises discovered pretty early on a nice example of it's a real analytic distribution that has no extreme value limit. So it's not at all the case that everything is going to have one of these limits, but it's also not the case that it has to be some pathological thing that, you need Cantor sets and so on to construct. And what happens is, I'll show you the picture eventually. When you compute the invariant, you see that it's beautifully cyclical. Right? It has no limit. It just falls into this lovely cyclic pattern. And of course, that's not a proof, because I didn't go to infinity, but I went out like so far that you're in the 1 trillionth quantile or something like that. There's no question about what's happening there. And I'm sure it's not hard to prove explicitly that will continue. But the other thing that we've been recently coming to grips with is that the magic of extreme value theory is it says that these limits exist. Okay? It doesn't give you a picture of how dense they are, if you like, in examples. However, when you look at real data, it's quite extraordinary how often you see that you get, applying these methods, especially our version of it, you get good approximations of what's going on with a tail fit to your empirical distribution of data. So that seems to be, now I think you can turn that into a theorem, but it seems to be a fact that that distributions that show up in real-world samples tend to be ones that have these tail limits, or at least they're close enough to ones that have tail limits that you can make good approximations by acting as if they did. And we have a very, very effective way of fitting these things that are in the Frechet family of tails. And for the longest time, we were just puzzled, really puzzled, by how well this stuff worked. And you could do it if you start looking at 20th century tropical storm records based on 50 years in the 19th century, you find that the average excess is exactly right. Almost, it's been a few percent, 6% I think, of being right. Rainfall over 100-year periods, daily rainfall, do the same thing. Take something from half a century ago and ask, what does it tell you about the biggest thing, bigger than what you've seen in that period? And the answer comes out very close to the right answer. Right. Now in the tropical storms, for example, as the data gets sparser, if you like, as you move from tropical storms to tropical storms that made landfall to tropical storms that caused massive damage, the accuracy of those predictions is still, I mean, if you get within 25% of that number using 50 years in the 19th century, I think that's extraordinary accurate. But of course, it's a lot further away than 6%. But that's sort of comforting that as the data gets rougher, you don't see the same precision in these estimates. But the fact is you see them all over the place. And, sorry? Oh, well, yeah, well, I mean, the most recent one is that we realize that there's typically, when as in England, the COVID settled into this sort of endemic phase where there were waves of Gompertz function growth followed by linear growth followed by Gompertz function growth. And same thing in Ontario, I guess. We noticed that you had about 3 weeks in the transition between those two things to try to figure out what was coming. Right. So you got 21 data points of hospital admissions, for example. The last 21, when things have been calm, and then it ticks up. So it's calm because you can project linearly and get a very good picture of what's going on. But all of a sudden, the slope goes up, and that means you're off on one of these curves again. We found that we could give very accurate estimates of how many people would be admitted to hospital over the next few weeks using 21 data points. Now that's if you ask an extreme value statistician, I'm sure they'll tell you that's impossible. And as far, none of the methods that you see talk about samples that small. Small is, when you've only got 500 points or 200 points or something like that. Right? So and that fact would have stopped New York City from being shut down. So it's not insignificant. Well, we don't know. We haven't. That was for the finance applications.
Everybody who works in machine value theory, except for the two people, at least kind of the reasonable people, they say, well, our methods work asymptotically, but in practice, we cannot rely on the estimates. You can get a kind of a ballpark estimate and such. So I think that you really shouldn't trust specific.
That's right. That's right. And this is one of the sort of conundrums of statistics, if you like. The body, statistical theory, has a lot of beautiful results that are proved on the basis of, mathematics. It's a theorem. If these conditions are satisfied, then the following is true. The problem is, of course, when you go to the applications, that your chance of proving that those conditions are satisfied is basically 0. So you're thrown back on checking how well does this actually work. You can't prove that it has to work. And in the situations where you can prove what will work, really hamper the applicability, right? Because it's a lot of conditions, a lot of requirements that have to be satisfied. So in a sense, you're always thrown back on checking that it works. You have data, you back test it. What else can you do? That's the right thing to do. But it's so what we've got is not. We've discovered lots of good reasons why it ought to be better than competing things. Like in financial applications, it's going to beat generalized Pareto distributions if you're looking at risk levels, anything that people would normally care about. We're more converged to the limit than the generalized Pareto will be there, for example. That's one sort of explanation. But the other thing is that it's a process that doesn't depend on theorems. So there's no theorem that says this should work if you have these conditions, except say if you, but in fact, so you're sort of starting right away with the part that the statisticians have to confront anyway. How do we know it works? Well, we've tried it, and in as much as we've got data here, we've tried it in subsamples and so on, and we get uniformly good results. That gives you confidence that it should work. Again, when we first discovered that we could do this with 3 weeks of data, I mean, with a constraint, actually it came from Ontario. There was a period where there was a lull between 2 COVID hospitalization waves, and it was only 3 weeks long. So that was I thought, okay, I know it's going to switch from linear to this other thing, but if I've only got 3 weeks, can I make any reasonable estimate? So that's why we used 3 weeks, and we found we could again and again and again. In fact, I think in New York, we would have used 10 or 12 days, something totally ridiculous, but the estimates. Well, right, but well, that's not a proof either, though, right? No, I mean, as a geometer, you believe that it should work, right? That doesn't tell you it will. You have to check. That's right. Yeah, that's right. No, we don't. The neighborhood will get too crowded. Anyway, that's some of the benefits of these techniques are that you can use things like this. The fact that I times j is an invariant, that actually gives you an intrinsic measure of the rate of convergence to an extreme value limit. Okay, because you just look at it at quantiles, and now you've got a discrete invariant, and that's a very powerful. I mean, there must be lots of good applications of that. Anyway, I'm going to. Well, yeah. Well, for some applications, yeah, that's right. I mean, that's another question is you can see using this stuff that the Pareto thing is converging to its limit at outrageous speed, right? Can you prove that you can't do better than that? I don't know. But that would be a nice result if you could. And it's quite probably true, unless maybe you could make No, I think it probably is true.
Yeah, it's true under some assumptions. The question is what is
Yeah, that's right. Yeah.
Because as you mentioned, right, so all these things also don't have limits, and you can
That's right.
in a way that needs not have a limit.
Yeah, yeah.
All sorts of funky things.
Yeah, no, you don't want to let the analysts in at the beginning. You got to keep them out until you know the answer. And then, because the thing is, I mean, there's no reason why that had to be the case. You see something that in principle, I mean, you can't even, there's no sensible statistical idea of what g to the lambda is when lambda is equal to pi, for example. What does that mean? With an n, you have an obvious statistical basis for it. It makes sense. But it doesn't matter what the theorem actually doesn't care about the n, so it doesn't care if you turn it into a lambda, and there you are, right? But yeah, there are I think there are a lot of interesting leads that could be followed. I think there are probably quite a few master's theses one could imagine coming out of some of these questions, and probably some PhD theses out of the answers to those questions and so on. But anyway, we'll see more of that as we go on. But I'm going to stop there for today. Any other questions? Okay, well, thanks for coming. Hope you come back. See you next week.